All right, everybody, welcome to day 2 of our new 40-day challenge. We're going to go deeper down the rabbit hole of oxidative stress that we saw in MedCram video, and we are going to talk about this electron transport chain a little bit more and these complexes and what's going on there. So we left off yesterday talking a little bit about ubiquinol and statins. So let's see what else we can pull from the video. I backed it up just a little bit so you remember where we left off.
Of electrons, and if there was no movement of electrons, the protons would not move across into the intermembrane space. So why is it important to have protons in the intermembrane space? Because the protons in the intermembrane space want to go back down into the matrix where there's a low concentration of protons. And so they go through a channel, and that channel is coupled so that as they pass through, just like a dam on the Colorado River turns a turbine, as these protons go through here, there is a coupling of ADP to, you guessed it, ATP. And we finally now have our currency. So how do we go from carbs, again, fats and proteins, to ATP? It gets metabolized down into 2 carbon units. The 2 carbon units goes into the Krebs cycle. The Krebs cycle turns it into electrons. The electrons then go to the intermembrane space, where as they go down the electron transport chain to increasingly more oxidized carriers, it finally gets to the most oxidized electron acceptor, which is oxygen, which then converts it into water. It reduces the oxygen to water. But in the process of this electron transport chain, we get protons, which are put into the intermembrane space. This builds up with a lot of concentration, and then it comes down from the intermembrane space into the matrix, coupling ADP into ATP, and now the body has energy. If, on the other hand, your cells don't get enough oxygen, then the electron transport chain backs up. Protons can no longer move into the intermembrane space. Therefore, you don't have a cascade coming down. Therefore, you don't have ATP, and the cell loses energy and dies.
Okay, I'm going to pause there for a moment. So you hear him saying, if there's not enough oxygen, there's a problem. There's a backup. What I want you to recognize, and in my opinion, as amazing as this explanation is, and remember, he is explaining this for the benefit of doctors. To make this very practical for you, I want you to keep in mind, again, Dr. Lee knows work. If he is the world's leading expert on mitochondrial health, the emphasis of his teaching in his book has to do with, and again, he mentions this, but it's not emphasized enough. For the end user, which is you, that backup, when it comes to being practical, is happening because you're eating too much food.
Yeah, it doesn't matter how much oxygen you have at the end of the electron transport chain if there's just a constant stream of electrons all the time. It's just pure logic. You can't accept all those electrons. You'd be using all the oxygen in your body to do that.
Exactly. So I wanted to pause there to make that clear, because again, the purpose of these MedCrams videos is for doctors to understand what's happening. It's not for the average user. But if we can pause a timeout and explain to you guys, yes, this is true, but how does it happen? From a practical standpoint, you're eating too much food. You're just, at the end of the day, you are in a surplus. We talked about fatty acid spillover. This is what we're talking about. This is also what leads to the oxidative stress from a practical standpoint. Well, let's just also remind you, what the heck, what's the purpose of mitochondria anyway? What is ATP? Why do we need it? What's the body's currency of energy, right? Just so we are always on the same page here, we're talking about energy.
ATP is used in so many biochemical reactions, probably all of them to some degree, where, not in every single reaction, but at least at the start of any cascade, you have ATP to initialize reactions, to give enzymes energy they need to do the transformation of one thing into another thing. ATP is everywhere, and it's used in all of those reactions. It's a very important molecule for that reason.
So again, the body is always trying to keep a regulation on things. So yes, it is important. How do we get it? We get it from food. And as Jordan explained in the previous video, you may say to yourself, well, why do we need energy to make energy? Well, one of the things that you also have to remember now is too much energy is not good. Because what will happen, again, from a practical standpoint, end user, for you guys, it's called body fat. That's what's going to happen. Okay, that's how you're going to store that extra energy. So let's go deeper down the rabbit hole and see what happens here, and we'll start getting into minerals and start talking there a little bit.
Intermembrane space. Therefore, you don't have a cascade coming down. Therefore, you don't have ATP, and the cell loses energy and dies. So, there are a couple points that I want to point out here. Number one, if you were to take a diet...
Well, let's just actually pause here for a minute. I'm going to replay just that last brief part again. Just listen again.
Now the body has energy. If, on the other hand, your cells don't get enough oxygen, then the electron transport chain backs up. Protons can no longer move into the intermembrane space. Therefore, you don't have a cascade coming down. Therefore, you don't have ATP, and the cell loses energy and dies.
Okay, so he just said, then the cell loses energy and dies. But, Jordan, is it always bad for cells to die?
No, it's not.
So this, again, this is not, remember, this is for doctors, not for end users. So this doctor already knows that doctors know, right? Why it's often good for cells to
he
die.
wouldn't disagree with anything we're saying.
He's not going to disagree. But let's just talk about what are we talking about? What's it called when cells die? And why do we want them to die?
So under two different contexts, right? So there's apoptosis, which is where a cell will commit suicide, cellular suicide, where it starts a signaling cascade that eventually results in the cell signaling for itself to die. This can happen for a couple different reasons. It can happen when a cell becomes very old. It can happen when a cell has damaged DNA that's beyond repair, so your DNA repair enzymes cannot fix it. It can happen if a cell becomes cancerous. It can happen for if it detects viral DNA in the cytoplasm of a cell, it can signal to destroy the cell. So that's called apoptosis.
Let's time out real quick.
Yeah.
Just confirm this.
Mm-hmm.
Our body is always creating cancerous cells.
Yeah.
And then it's dealing with it through exactly what you're talking about.
Apoptosis. There's a bunch of there are several pathways in cells that allow the cell to signal for itself to kill itself. The STING pathway is one that specifically looks at viral DNA, bacterial DNA inside the cell, because if there's any type of fragments of DNA or proteins in the cell that aren't produced by the human body, the cell is probably being invaded. So we evolved this pathway that detects fragments of DNA, that detects fragments of proteins that are in places they shouldn't be, and that signals for the cell to be destroyed. So that's one of the pathways.
And now what's the other pathway?
The other pathway is called autophagy.
Now let me ask you a question.
Mm-hmm.
Does fasting cause autophagy?
Yeah. It's fasting, even for a few hours, like intermittent fasting, increases autophagy.
About 18 hours, you're going to start seeing cellular autophagy. That's why intermittent fasting is good, closing that eating window is good. But why is it good? Why is cellular autophagy good? Because if you just watch this video and you hear what the doctor just said, you're going to assume, oh my gosh, my cells are dying, this is bad. Well, let's talk about the context here and why it's not always a bad thing.
So autophagy, auto meaning like itself, and phagy meaning eating, literally means self-eating. What it's doing is your cells are being consumed by other cellular organelles and components that recycle the components of the cell and reuse them. This is important for senescent cells that, so senescence essentially means that a cell is continuing to exist. It's not dividing. It's not providing anything for the body. It's kind of just sitting there.
Yeah.
It becomes this immortalized blob, basically. It's not doing anything to help you.
If there's a woman by the name of Judy Campisi, if you want to look her up, she was interviewed by Dr. Rhonda Patrick. She is one of the world leading experts in inflammation, and one of the things that she talks a lot about is exactly this, which is cellular senescence and why it's such a problem. So we really want these cells to die.
So these senescent cells can be destroyed through autophagy, where so if a cell is senescent, it's not going to undergo apoptosis. It's not going to signal for it to be killed. This is why autophagy is also important, because then the cell can be killed by other cells. It can be recycled, broken down, and it's not there essentially taking up space. Because if you have a whole bunch of cells that are senescent, like in a group together, they're not going to be doing the functions that normal cells would be doing. They're not going to be having the same benefit as other cells. So you need to clear these things out every once in a while.
Excellent. So is fasting the only way to create cellular senescence?
To decrease cellular senescence?
No, I'm sorry. I said cellular senescence. I'm sorry. To create autophagy.
No, there's other ways. There's the sirtuin pathway is one of the popular ways that people are looking to increase longevity through decreasing cellular senescence. Sirtuin, things that activate sirtuin pathway activate autophagy to decrease cellular senescence. There's a lot of things that seem to do that in test tubes. Less things that seem to do it in the body. Some of the main ones are pterostilbene and resveratrol. Those are the two big molecules. Pterostilbene is essentially just more bioavailable resveratrol at the end of the day. Green tea, catechins from green tea. Coffee seems like it activates autophagy. In fact, coffee activates autophagy a lot in rats. Dark chocolate. Grapeseed extract.
Did you hear Jordan said dark chocolate?
Dark chocolate,
not
Hershey bars.
Hershey bars. Dark chocolate would be 90% or more, everybody.
Yeah, so there's lots of things that activate that pathway through sirtuins. I'm sure there's a lot more.
What about exercise?
Exercise. Oh yeah, right. Sure. So things that aren't supplements, things like exercise would absolutely increase cellular autophagy, and also oxidation.
Excellent.
Yeah.
So that's what I was going to go next. So now it may be, some of this may start to seem counterintuitive to you, and this is why it is so important that context matters. And I don't know what he's going to say in his next video yet, but we'll find out. All I know is what he says in this video. But what I do want you to understand, and we'll have Jordan explain this a little bit more. So if we heard him just say that it causes the death of cells, it sounded like a bad thing, right? That's why I played it twice for you. But now we realize, well, wait a minute, that's not a bad thing, but it depends on the context. This oxidative stress this autophagy is a good thing. Well, why is it good? Well, we just explained why, right? It's one of the ways that we get rid of stuff in the body that we don't want. That's understandable. And we're telling you that one way to do it is, yes, through certain foods, yes, through fasting, yes, through exercise. But you may say, well, geez, exercise causes the dying of cells. It just sounded like a bad thing in this video. Man, it's not a bad thing. You know what else exercise does? It increases oxidative stress. So why in the world would it be a good thing to increase oxidative stress in the context of exercise?
Well, sure. So oxidative stress in small amounts upregulates the production of antioxidant enzymes. So you get a bigger return of antioxidant protection for this small investment.
So you're telling me that you're teaching your body something?
Yeah, you're training your body essentially to deal with this amount of oxidative stress in a more beneficial, healthy way.
So your body can learn to deal with oxidative stress if you train it.
Absolutely. And the other thing is that we were talking about in the previous video how oxidation is actually extremely important for the mitochondria, for the electron transport chain. So if you're constantly in a state where you have super high antioxidant capacity in your bloodstream, if you're constantly eating antioxidants and you're not exercising and you're not moving and everything like that, you're not going to create an environment that's conducive to producing this ATP because you're already in such a reduced state. So it's something else to consider, is that we do need oxidation to some degree.
Excellent. So I think that we'll go a little bit longer. We'll get to about that 20-minute mark. So let's check out what's next.
I want to point out here. Number one, if you were to take a diet with quick metabolism of carbs, fats, and proteins, you would find yourself with a surplus of electrons ready to move to the electron transport chain. Even though this is a regulated series of metabolism, you can see there a high carbohydrate, high fat diet will quickly give you many electrons in the matrix of the mitochondria. So there is some good data that excessive high caloric intakes from either a high carbohydrate or high fat diet will cause more of these 2 carbon units to go into the mitochondrial Krebs cycle. And then what will come out are more electrons, of course, which go to the electron transport chain. That's number one. Number two is that oxygen is ready to accept any kind of electrons. It's ready to accept electrons down here in the electron transport chain. And if it's ready to accept electrons here in the electron transport chain, it could certainly accept electrons anywhere along this path, because more than any other species in the body, it loves electrons. Fortunately, these electrons are kept in the form of NADH and FADH2, which is fairly tightly regulated. But sometimes if there's too much NADH or FADH2, that can go awry.
And let's stop
The next
there.
thing that we need to talk.
So, and we'll end the video talking about what you just heard. So first, he talked a little bit about carbs, fats, and proteins, and he talked especially about carbs and fats, basically too much. This is the first time he talks about a calorie surplus. And you may say, well, why didn't he say carbs, fats, and proteins? Why just a high carb, high fat diet? Again, this is a doctor explaining to other doctors. I will tell you guys this, okay? Context of these things matter. Remember, that's why we took the time to talk to you guys about what type of carbs, okay? What type of fats, what types of proteins, why do they matter? And I assure you that they really matter here. Things like controlling insulin really matter. Things like nutrient density really matter. Things like chewing your food and taking your time to eat and all these things matter. So in the context of high fat, high carb, I want you to think about the average American diet. What are they eating? Okay. Well, again, you have to understand that when science takes data, they're taking from what the average is. Okay. What is the average in America? Look at the average fiber intake in America. It's pitiful. It's pitiful compared to what we should be getting. If you eat a low fiber, high sugar, high fat diet, I promise you, you're heading in a bad direction. And when you make it a calorie surplus, it's even worse. And this is what leads to that backup of that electron transport chain. So I want you to be clear. You may be saying, well, fats are bad? Carbs are bad? No. What's bad is the wrong types of carbs, the wrong types of fats, not having enough protein in certain contexts, depending on who you are and how much exercising you're doing and whatnot. You got to remember, not to go down a pathway here, but if you're somebody that exercises and weight trains, your body really needs protein in order to rebuild. If you're somebody that's injured or has injury, your body really needs protein to build. So in the context of these macronutrients, meaning proteins, carbs, and fats, they all do certain things, and they all do certain things really, really well. Again, the average population, super low fiber, super high sugar, so way too many carbs in the wrong form, and bad forms of fats, okay? And then he talked about a little bit more about how oxygen can become deleterious in these complexes, and that's what we're going to talk about tomorrow. And I think that you'll find that super interesting.
I just want to add a little bit. I think part of the main reason why he doesn't mention overeating proteins is because of how inefficient they are in terms of energy and being utilized in the Krebs cycle compared to carbs and fats. When you eat a protein, it's presumably not in the form of free amino acids already, unless you're eating like a protein shake that's already like fermented into them or whatever. And even if they were, those amino acids are not as readily available to produce energy as fats and carbs are. Carbs are either chains of sugars or simple sugars. Fats can be broken down into free fatty acids and glycerol, which is also a type of carb at the end of the day. Proteins have to go through gluconeogenesis, which is a process that takes energy in of itself, and it's not always fully broken down into its constituents anyway. So overeating protein is not usually the issue with mitochondrial health. It's usually overeating carbs and fats and the wrong types of carbs and fats.
Right. And that's why, if you guys remember, in the UTC manual, phase 1, we purposely have you overeat protein for a while, and then we start to dial things in as we navigate through the different phases, phase 1, 2, 3, and 4, and implement some of these strategies. So that's enough for today. Thank you for your time, and you'll hear more about what's going on with oxygen in between these complexes tomorrow.